Okay, what we want to talk about now for the next, the end of this lecture and a little bit for the next lecture is to kind of give an overview of some of the tools we'll need to use to solve analytically some of these equations that we're going to be talking about with diffusion. Let's take an example to start. Suppose we have a kinetic expression or a kinetic experiment where we have a molecule O going to, say, a molecule R. And we can characterize that reaction with a rate constant. And our rate constant is given expression where we have the concentration of species O with time has changed with time, and we want to get the change of the concentration of O with time. And we can write that that expression is equal to the rate constant times OT. Well, we can solve that by using the techniques that you've learned with ordinary differential equations to know that C sub O is equal to a constant times an exponential E minus KT. And I won't discuss that any further. You can review that. Calculus book should have that in there. The problem we have with diffusion equations is that often they're partial differential equations. So these partial differential equations have two or more dependencies, which make them not amenable to solving them the same way that we'd solve by ordinary differential equations. There's more than one form of the solution, and the solution isn't obvious from the form of the equation, unlike ordinary differential equations. For example, we have this equation here for the concentration of O as a function of x and t, with dt is a function of the second derivative of the concentration O xt over dx squared. So here we have a partial differential equation with x, time, and space in the system. Now, a solution to these equations are given by boundary value and initial conditions. So in general, the form of the solution that we're going to have is strongly dependent on the boundary values that we apply to the system. And that's the critical thing we're going to be learning about in the next lecture or so. So what we're going to try to do is try to show you very briefly, and I'm not an expert in these sorts of problem solving, so but we can learn a little bit about solving these sorts of problems by reviewing the mathematical treatment they give in Appendix A, which is a primer on solving boundary value problems using the Laplace transform. The thing to remember is that mass transfer is not chemistry, so we're really not very chemically oriented when we're talking about these sorts of problems, but we have to understand the process of mass transfer to understand a lot of times the chemistry that's going on in our system. Usually, for example, we're going to be, like I said, we're going to be interested in these two equations, or the second law, fixed second law, and the first law, which is the current or the flux relationship. Species O, for example. And we're typically, for our fixed first law situation, we're going to be considering the situation at the interface of the boundary between the electrode and the solution. So really we're only interested in the flux at the interface and the fixed first law. Now we need an initial condition to solve these problems. Typically for t equals 0, what's the form of the solution or the form of the system at t time equal to 0? And we need two boundary conditions. For example, two boundary conditions. For example, our initial condition might be such that, say at t equals 0, we can write that the concentration of species O at at time equal to 0 at some point in solution is equal to the bulk. And species R at some distance is equal to concentration of R in the bulk. In other words, at time 0, there's no difference. The concentration of species O and R are the same throughout the solution. So that would be a good example of initial condition that we often see in electrochemistry, that the solution is has a uniform concentration. But that's not the only type of initial boundary condition we might have. Sometime, for example, we might have a boundary condition where the initial system was having a concentration of x at time equal to 0. That's some function of x. In other words, it may vary throughout the solution somehow. Maybe sinusoidally the concentration varies. That'd be a very unusual situation, but it could possibly happen. For boundary conditions, usually there is some sort of distance condition. For example, what's happening as x approaches infinity would be a good example of a distance condition. You might specify that at the limit as x approaches infinity in these systems, that the concentration of O, as a function of x and t, is equal to the bulk. In other words, it doesn't really matter what's happening at the interface of the electrode solution interface, but in the infinite distance away from the electrode or close to it, we regain the bulk concentration. And of course, we could write a similar expression for species R. Okay. Now, these are just examples of boundary conditions. These are not necessarily the boundary conditions. These are often these two boundary conditions, though, are often called the semi-infinite boundary condition. But another distance condition might be, for example, at some distance L, there is a wall in solution, and that would be, say, a thin layer system where we have, instead of an infinite extent of solution, we might have a wall where the reaction is occurring. So this would be a thin layer system. And that has very different properties in a semi-infinite condition. Usually the third boundary condition is a description at x equal to 0, or at the interface. We talked about x being 0 and time equals 0. Here we have x equal to 0 at some time. One type would be that the concentration of O at x equal to 0 at any time is equal to 0. In other words, the species O may be present in the bulk, but at the interface is 0. This is a particular form that's given a name called a Cottrell. It ends up being used in the Cottrell equation, which we'll talk about next time. Or we might have a condition C sub O T, where the concentration of O at the electrode interface is some function of potential. And that's a moving boundary condition problem. And those are very difficult to solve, although not impossible. So those exist. Another possible, a popular type of boundary condition would be a flux or mass conservation type expression, where we say that the species of O is equal to the species of R or the flux of species O is equal to the negative flux of the species R at any particular time. Okay. So in order to solve these partial differential equations, we're going to use the concept of transforms. And transforms are used all the time in mathematics and in real life. You use them in conditions where you may not even understand what you're doing. Often the transforms are used to linearize problems or make them simpler and to reduce the dimensionality of the problem. And a good example of a transform is, suppose we wanted to solve the multiplication 4 times 5. Well, we may know by rote the answer to that problem, but we could use a transformation system to make the problem into, rather than a multiplication, into an addition system. For example, if I take 4 times 5 and transform it into logarithmic space, we can make in the transform space, this equation be true. Log of 4 times plus the log of 5 is equal to the log of our answer. Let's call it z. And since all we need to know is log of z, once we do the inverse transform, we can return to normal space and find our answer. I put 6 there. I don't know why I have 6 on my notes. All right. So that's an example of a transform. Laplace transform is no different. We're just using a different form of the transformation. That's not on our calculator, unfortunately, to do the Laplace transform. So I think I skipped the page here. No, I guess not. Okay, well the idea would be, for example, in an ordinary differential equation, we could say, let's say I want to solve my ordinary differential transform, or ordinary differential equation, and it was solved for t. What we can do is we can make it and convert it into the Laplace space, where we transform time derivatives into s quantities. Time goes to s. And then we solve for s in our particular problem. And we'll see why that makes that easier to do in a minute. For example, if we have an expression where we take the derivative of y with respect to t equal to minus kt, if we do the Laplace transform, sometimes LPT or sometimes the script L is used, we get an algebraic equation. To solve, where y is some function of s is equal to our system. We can solve that algebraic system, take the inverse Laplace transform, and get our function of y with respect to t out of the system. Similarly with partial differential equations, we make it into a simpler situation. Usually we turn a partial differential equation into an ordinary differential equation. We can solve that ordinary differential equation in Laplace space, then transform it back to get our solution of our partial differential in real space. Well, we're running out of time, but let's just give you a brief idea of what we're going to be doing when we do Laplace transforms. The idea of a Laplace transform is quite simple. We just use an integral transformation. We can have some function of time, and function of time may be something as simple as a constant, or it might be something like an exponential function kt, e to the minus kt, or so on. The Laplace transform just takes that function of time. Usually they use the curly braces here. And use a large f and a t of sub parentheses t, and then we use a small f parentheses s, which is equal to an integral from 0 to infinity e to the minus st ft dt. Can you get that, Rob? So let's take an example. Let's suppose we're taking a Laplace transform of A. A is our function of t. That's equal to f sub s. That's equal to the integration of 0 to infinity e to the minus st. A is our function of t dt. And that equals a times the integral of 0 to infinity e to the minus st dt. We do that integral, we see that this is the result, and we evaluate that from infinity to 0, and we get the result of 0 minus a over minus s. So in other words, if we make a little table here, a in Laplace space is equal to a over s or a in time space is equal to a over s in Laplace space. Let's do another example. Let's suppose we take the Laplace transform of e to the minus kt. Well, that would be equal to the integral of 0 to infinity e to the minus st e to the minus kt dt, which equals to 0 to infinity e to the minus s plus k dt. After we do the integral, we find that that would be e to the minus s plus k t over minus s plus k. And then we evaluate that again from 0 to infinity. Minus this would be the result. In other words, e to the minus kt is equal to 1 over s plus k in a Laplace space. T, function of t, if it's t, would just be equal to 1 over s squared. All right. The book has some other examples of Laplace transforms that you can look up and apply those directly. And of course, you can always do the integral yourself. Sometimes it's hairy to do the integral. In fact, certain programs will do the Laplace transform for you symbolically. I know MathCAD will do Laplace transforms, and I think Mathematica and Maple also do those. So you can use those math programs to do those things for you. What we're going to try to do is just have you do a few of them by hand to get you used to the idea of doing it. And we'll have you do some in the appendix, and then a couple of applied problems just to give you some feeling for it. Next time we'll go through a few examples of doing Laplace transforms of derivatives, ordinary differential equations, and partial differential equations. And then we'll go into solving some actual diffusional problems and using Laplace transforms and what we've learned. All right. We won't always be able to use Laplace transforms. Sometimes we'll have to use simulations or numerical methods to solve the problems. And we'll see that too the next time.